Hi class, this is Mr. Morris, and this is the last video talking about the periodic trends of the elements. We want to do a comparison of subsequent ionization energy. So what that means is every time you remove an electron, it requires more energy. So after you remove the first electron, it takes more energy to remove the second, and it takes even more energy to remove the third, and so on. We want to talk about the reason. The reason for that is that removing an electron from a neutral atom requires less energy than removing an electron from a positive ion. I hope that makes sense. The positive charge is more attractive to a negative charge than if it's just a neutral atom in general. So it's harder to pull those electrons away when it's a positively charged ion. Also, you can think about electron-electron repulsion. Remember, each time you take an electron away, you have less electron-electron repulsion if we're looking at the same number of protons and the same number of energy levels. So as the ionization energy values increase, some increases are much higher than others. Take a note that a huge jump of ionization energy values happens if the subsequent removal of electrons is from another principal energy level or from the core. So once we get the last valence electron taken out, it takes a lot more energy to take the first core electron. And that's a useful tool in identifying how many valence electrons a certain atom has. Look at this table right here. That staircase that you see, that represents the division between the valence electrons and the core electrons. So we're going to take Si as an example and look at it. The big IE jump happened between the fourth and the fifth ionization energy. So if we look at Si, right here we have 700 going up to 1500. That's a jump of somewhere around 700, 800. Then it jumps up again. This time it jumps up about 1500. That's notable. And this time it jumps up somewhere around 1000. Not that big. Then it goes from 4000 to 16,000. That's like 12,000. An increase of 12,000. That is the largest jump of any of the increases for silicon. This means the first 4 electrons removed are from the outermost energy level. They were valence electrons. And the 5th electron removed, and all of the ones after that, came from the core levels. They were the core electrons, the ones that were not in that outer energy level. They weren't valence. Let's use distance and shielding to explain the jump. So how can we conclude, and using distance and shielding to explain the jump, once you go down an energy level, then all of those electrons are closer to the nucleus, so it's harder to pull them away because the closer the electron is, the stronger the attraction to the nucleus. Also, they have less shielding because there's one fewer energy level to shield them from the effective nuclear charge of the nucleus. Distance is the best way to explain this because you don't risk the chance of misusing the word shielding and lose points on the AP exam. How can you conclude that sulfur, S, has 6 valence electrons, looking at this table? So we find sulfur. Well, this is an increase of 1,251 when we take away our second electron. It's about 1,000 more to take the third one. It's about 1,000 more to take the fourth one. Then about 3,000 more. Then it's about 1,000 more. Then it's nearly 20,000 more. It's about 19,000 more kilojoules, I believe, is kilojoules per mole to remove that 7th electron, the 7th electron from sulfur. So the 7th ionization energy is extremely high. The jump in ionization energy from the 6th electron to the 7th is much larger than any other increase in ionization energy. That's one way of explaining it. Excuse my writing on that, but the jump in ionization energy from the 6th electron to the 7th electron is much larger than any other, so that tells us we have 6 valence electrons. That 7th one is a core electron. All right, we want to observe the following table. We're going from 801 to 2,427. That's a pretty big jump. It's a little over 1,000. Then we go up to this, which is a little over 1,000. Then we go up to this. All right, that's over 20,000. And then going to the next one, it's around 10,000. The biggest jump is between the 3rd and 4th. So that tells me that there are 3 valence electrons in this. That crossing from the 3rd ionization energy to the 4th ionization energy is the largest increase. So based on this data, we could say that the element has 3 valence electrons. The 4th valence electron took a lot more energy. The 4th electron took a lot more energy to remove, so it is not a valence electron, it is a core electron. If this element is in period 2, what's the identity? Well, if it has 3 valence electrons, we want to look in group 13 on the periodic table for period 2. So period 2, 1, 2, 3, boron is the one in period 2 that has 3 valence electrons. So we can scroll down. We could say this element is boron. Now let's take a look at the exceptions to some of these ionization energy trends. There are a few notable exceptions we want to talk about. In general, going across a period from left to right, the ionization energy increases. We know that the reason for that is because the number of energy levels stays the same. But the number of protons increases. Number of protons increases. As a result, the attraction between the valence electrons and the nucleus will be stronger and ionization energy increases. Those electrons are held a lot tighter because we have more protons in the same energy level. They're held on tighter. That's the general trend. However, there are 2 general exceptions seen on each period, and we want to look at period 2. So period 2 is represented by this, by that curve. You notice that mostly we're going up, but there are 2 noticeable exceptions. We have a dip right here. We have a dip right there. Let's talk about what those are. It's the 3rd and the 6th element. Let's compare them. Explain why the first ionization energy of beryllium is greater than the first ionization energy of boron. That's the opposite of what you would expect. It gives us a little hint here and says to write the electron configuration for each. And we want to think about the amount of energy that's needed to remove an electron from each element. So let's look at beryllium and boron. Beryllium is right here. That's 1s2, 2s2. And then boron is over here. 1s2, 2s2, 2p1. Let's write that out. Boron is 1s2, 2s2. And I'm sorry, that's actually beryllium. And boron is the one that is 1s2, 2s2, and then 2p1. Now let's think about the energy levels we have and where it's the hardest to take electrons from. So I've got more protons as we go across the row still. But if you look at this, I've got a 2s sublevel. That's where my last electron is. And over here I have a 2p sublevel. That's where my last electron is. What I want you to know is it takes less energy to remove the first 2p electron than it does to remove the last 2s electron. We've got a higher principal energy level, or a higher energy level when we get to the 2p sublevel. So it's a little further out. It's easier to take one electron away from 2p than it is to take that electron from the 2s sublevel. So that's why we see a little dip in energy as we go from beryllium to boron. So again, basically what we're saying is it takes less energy to take an electron from the 2p orbital, from a 2p subshell, than the 2s subshell. That's why when you go from 2s2 or 3s2 to 3p, when you go from the s sublevel to that first electron in the p sublevel, it's going to be a little bit of a dip in energy because it's slightly easier to take that electron out of the p sublevel than it is to take it out of the s sublevel. You've got a little bit of shielding that takes place, shielding the p sublevel from the s, because it's a little higher in energy. All right, we want to explain why the first ionization energy of nitrogen is greater than the first ionization energy of oxygen. So we're going to write our electron configurations again, and we're also going to do the orbital diagrams for this one to explain it. This is if you are comparing, electrons within the p orbital. So the second exception, we're going from nitrogen to oxygen. So that's going to be 1s2, 2s2, 2p3 is our first one, and then it'll be 2p4 as the other one. 1s2, 2s2, 2p3, and then 1s2, 2s2, 2p4. Okay, this is for oxygen, and this is for nitrogen. All right, let's write our orbital diagrams as well. So for nitrogen, 1s, 2, we have 2s, 2, we have 2p. Remember, for p we've got 3 orbitals. We've got to follow Hund's rule, so we have 1, 2, 3, just up arrows. When we get to oxygen, we're going to follow Hund's rule again, 1s, up, down, 2s, up, and then down, that's a down arrow, and then 2p, still following Hund's rule, we go up, 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 and then down. Okay, so at this point, we have, on the right-hand side, for oxygen, we have some paired electrons. Okay, so on the left, all the p orbital electrons are unshared. So all 2p electrons in nitrogen are unpaired, but in oxygen, one orbital one p orbital, I guess I should say, is filled with a pair of electrons. Okay, this leads to electron repulsion, which makes it easier to take away an electron. Makes it easier to remove an electron. In other words, what we're saying is ionization energy actually decreases because it's easier to take that electron away. That pretty well sums up our periodic trends notes. We've got some practice, and we will talk about the practice in class next time.